Hello my esteemed viewers. In this tutorial, we will go through very clearly as to how we can draw bending moment and shear force diagrams specifically to simply supported beams considering all kinds of loads. So as a first example, we have a simply supported beam of span 4 meters and a central load of 40 kilonewton. So as it is, the loading is symmetrical, and our first step is to find the reactions. Since the loading is symmetrical, we will have half the reactions, half the load being shared by both the supports. Therefore, RA equal to RB, both of them are equal, which is equal to 20 kilonewton, which happens to be half of 40 kilonewton. Now, as a second step, we will just go through how we can draw shear force diagram after computing shear force values at various points over the beam. And we have 1, 2, 3 points. And when we move from right to left over the beam, we will find, and we are not supposed to take a section over the supports because that would mean cutting the support. Therefore, we will just come to the left of B. So SF just to the left of B equal to 20 kilonewton, because 20 kilonewton, which is positive going up, prevails over here. And here is the section. Here is the section just to the left of this, and this just is very, very small. And when we start plotting, this just to the left will become the same point. And there are no other effects, there are no other forces over this stretch of the span, that is half the span. Therefore, shear force remains to be 20 kilonewton till to the right of C until here. And therefore we have avoided the 40 kilonewton to be considered when we just say just to the right of C. And when we move just to the left of C, we want to involve the 40 kilonewton effect, that is the applied load effect. And that outsmarts, because this is negative and this is positive. There is a positive shear force due to the reaction, and there is a negative shear force due to 40 kilonewton. So that becomes SF just to the right of C is 20 kilonewton, of course, and SF just to the left of C is 20, the positive shear force, positive reaction, and shear force due to this positive effect, and minus 40, that will give us minus 20 kilonewton. And this minus 20 kilonewton will prevail just to the right of A. And just to the right of A, we have minus 20 kilonewton. So, and this is the diagram. At B, it is 20 kilonewton positive, and it will continue till to the right of C, and to the left of C, it becomes negative, and this negative shear force continues till A. So therefore, we have two zones over the beam, where half of the beam is subjected to positive shear force and half of the beam is subjected to negative shear force. And here at this point exactly, the shear force becomes 0. And we will start drawing our bending moment diagram. First of all, we need to compute, and here again we need to consider important points. It is A, B and C. A is a simple support, B is a simple support, and C is the point where loading appears. And as far as bending moment at B is considered, it is 0 because the beam simply rotates with respect to the support. And this simple support, this being a simple support, there runs a pin, and if we try to apply the moment, the beam entirely will rotate. And therefore bending moment at B equal to 0. So this is a problem wherein we have understood whenever we encounter simple supports, we will just say bending moment at simple supports equal to 0. And we will move to the section C. As I told in the previous tutorial, there is no question of considering just to the right of C and just to the left of C, because when we compute the bending moment, distance matters. The distance, the span of the beam will become the momentum, which will create the bending moment. Therefore, here at C we have the effect of the reaction, the 20 kilonewton, and 20 kilonewton will lift the beam up, creating a kind of sagging. Therefore, the bending moment at C is 20 into 2, 40 kilonewton meter, because according to our sign convention, sagging bending moment is positive. And at A, the bending moment here is 0, bending moment at C is 40 kilonewton meter, and at A it again becomes equal to 0. And this is to be connected. These points are to be connected. So let us see why it should be connected by a straight line. Because if we consider bending moment at any section randomly over here at a distance x, we will have 20 into x is the bending moment. So if bending moment were to be y and the value were to be 20 into x, it looks like y equal to mx. Therefore the relationship of the with the load as far as bending moment is concerned, and if the load is concentrated, the bending moment happens to be linearly varying, because it looks like y equal to mx. So here bending moment equal to reaction into x, 20 into x. And eccentric concentrated load we will consider as over a simply supported beam as the second example. So here is the beam of span 4 meters and here is the load which is eccentrically applied. So now the reaction value changes. This support will have more reaction when compared to this support, because 30 kilonewton is very near to B. So we will just find it out by our usual methods. We will apply RA plus RB equal to 30. While writing this particular equation, we will have used sigma Fy equal to 0 as one of the fundamental equations of statics, which will keep regard for the equilibrium of the beam. And this is sigma ma equal to 0. We will take moment with respect to this a equal to 0. In order to take moment about a, this support is to be released and this force is to be applied. The reaction force is to be applied. Reaction RB into 4 is an anti-clockwise moment, and 30 into 3 is a clockwise moment. We will just equate RB into 4 equal to 30 into 3. Or we could have written this like an equation, minus RB into 4 plus 30 into 3 equal to 0. This is one and the same. Therefore, we will get RB equal to 90 by 4, 22.5 kilonewton. And if we just substitute value of RB in this equation number 1, we will get RA. RA equal to 30 minus 22.5, so that will give us 7.5 kilonewton. We will just calculate shear force values at various points of the beam as a second step. So here just to the left of B, the first point is just to the left of B. It is 22.5 kilonewton. It is positive because it is going up, and the section is here, and this is the value. We are simultaneously plotting this value, and this value continues just to the right of C. Just to the right of C, it is 22.5 because there are no other intervening forces. And just to the left of C, it is 22.5 till here and minus 30 because this load is going down. Therefore, it becomes 22.5 minus 30 minus 7.5 kilonewton. So the shear force will come down with a negative effect, and the same negative effect will continue just to the right of A because there are no other intervening forces in the span portion AC of the beam. And this happens to be the shear force diagram. And you should notice in the shear force diagram, wherever the shear force changes its sign from positive to negative, there is a step that is created, and this step is having a value of, or having a drop of, having the magnitude of 22.5 here till here plus 7.5. Therefore, the total height of this particular drop will be equal to the applied load. So this is a very important point to note down. So whenever beams are loaded with concentrated loads, the variation of shear force at the location of loads will be equal to either a rise or a fall, and the total amount of rise and fall total together will be equal to the intensity of the load that is being applied at that particular point. So SF just to the right of A is minus 7.5, and here the reaction is 7.5 positive, and we have got a negative shear force. So this is a check for we having done this problem correctly. And when we start drawing the bending moment diagram, we will calculate bending moment at B, okay, bending moment at C, and bending moment at A. Bending moment at B is going to be 0 because it is a simple support. Bending moment at C is reaction into 1. and this is the reaction, and this is the section, and the reaction will just lift the beam up, creating sagging. Therefore, bending moment at C is 22.5 kilonewton. Bending moment at A is 0 because it's simple support. We will just plot this. Bending moment at B is 0. Bending moment at C is 22.5 kilonewton meter, and and it is connected by a straight line because the variation is a straight line. It looks like y equal to mx, where y is bending moment and mx is m is the slope and x is the distance where section is taken, and here once again it becomes 0, and this is a positive bending moment distribution diagram. So the maximum height is 22.5 kilonewton. Here again we notice whenever concentrated load acts at the just beneath the concentrated load, at the point of concentrated load, the bending moment tends to be maximum. And if we have a number of such loads over here, the bending moment is going to be maximum at beneath the load which is maximum of all the concentrated loads. So this is the bending moment diagram, and we will consider a beam subjected to concentrated load, and one among them is inclined load. So whenever inclined loads are acting over the beam, it is enough if we consider the vertical components. So here it's enough if we consider 40 sin theta which is acting downwards, and 40 cos theta which is acting rightwards has no effect as far as bending moment is concerned. But however it's going to generate reaction at the hinged support in an opposite manner. So here the horizontal component in this direction, and horizontal component, if this were to be a hinged support in this direction as opposing this horizontal force, will create a sort of compression in the beam. Anyway, that is, we never compute the compressions that are happening in a beam because it is out of context. We tend to focus on the variation of bending moment and variation of the shear force. And this is 40 sin 30, 20 kilonewton is only considered, and we can forget, we can be unmindful of the horizontal component of this 40 kilonewton. So we will find the reaction once again. RA plus RB equal to 20 plus 40, it becomes 60 kilonewton. Here again we should notice that only vertical component is considered, and we will take sigma MA equal to 0 because we have not solved the RA and RB. We will take MA equal to 0, that is the moment of all the forces, algebraic sum of all the forces, moment of all the forces about A equal to 0. So we will release this support and we will apply this particular reaction. We don't know the reaction, therefore it is RB into 6, which is anti-clockwise, equal to 40 into 4, this clockwise, and 20 into 2. We will get 200, and RB equal to 200 divided by 6, we will get 33.33, and when we substitute RB over here, we will get RA to be 60 minus 33.33, 26.7. So we have written the reactions. Now it is time for us to compute shear force. So shear force just to the left of B over here, it is positive 33.33 kilonewton because this force is going up, and the same force will continue just to the right of D because there are no other intervening forces. So it is 33.33. We will just cross this D and we will consider what is the shear force just to the left of D, and it happens to be 33.33 till here minus 40, it will give us minus 6.67, and minus 6.67 will continue just to the right of C because there are no forces between C and D. And it continues, and we will just cross this C in order to consider the effect of 20 kilonewton. 20 kilonewton being negative going down, therefore it will add to this 6.67. Shear force increases to 26.67, and this 26.67 continues just to the right of A, and we happen to see the reaction at A is 26.67 positive, and the shear force what we have got is negative. Okay. And here I think we need to write it to be negative. Negative sign is missing, and we will just add that. Yeah, 26.67. Here it is. We will make it negative. This is negative. Yeah. So SF just to the left of C, left of C is minus 6.67 minus 20, again minus 26.67, which happens to be, and that is the same to the right of A. Therefore we have the reaction to 26.67 positive, and we have got the shear force negative 26.67. therefore our computations are correct. And now we will just compute the bending moment. Here again, while computing the bending moment, we have C and D to be the predominant points, and at A it is 0, at B it is 0, because they are simple supports. Yeah, we will just start computing. This is the shear force variation diagram. This is the reaction. The same reaction continues, and it becomes negative owing to addition of 40 minus 40, and the same value will continue till here, just to the right of C, and just to the left of C it increases, and it increases to the extent of 26.67, which happens to be the support reaction at A. And here we can notice there are two steps coming, one here and one here, and the value of this step is 40 kilonewton, and the value of the step here is 20 kilonewton, and the variation is a stepped function. So 33.33 minus 6.67, this portion, and this is and from here till here it is 26.67. that is this particular step. Therefore it's a stepped variation. As far as shear force variation is concerned, for a given set of concentrated loads, it is a stepped variation. It looks like a staircase step, the step height being equal to the magnitude of the load which is acting just above those steps. Step height is equal to the load at all the points. We can notice. So we will go for bending moment computations, and we know the reaction. Bending moment at B is 0, it's here, and bending moment at D is the reaction 33.33 into 2. It is positive because it's going to lift the beam up, creating some shape of a saucer, which would tantamount to the sagging bending moment, and it is 66.66. and as we move along, and the bending moment at C is, we can come from this side. There is no need to come from this side, traversing all the way from this support and covering this particular force, etc. We will come from this point and we will apply the principle. And if we consider this portion of the beam, and if we come from the left, it is only the effect of reaction. Therefore the reaction is 26.67, which is going up, and it will lift this particular portion up, creating sagging bending moment. It is 26.67 into 2, that is 53.34. and it's over here, and this is 66.66, and this is 53.34, and we can notice at the bending moment is maximum just beneath one of the concentrated loads, and the concentrated load also happens to be maximum among the two, and we will connect them in a straight line fashion, because the variation of bending moment as far as concentrated loads are concerned between two concentrated loads happens to be linear. So this is the bending moment diagram. So simply supported beam loaded with two concentrated loads is in its entirety is sustaining positive bending moment of varying nature. Here it is 66.66, here it is 53.34. Therefore entire bending moment diagram happens to be positive. We will consider the fourth problem, which is bending moment and shear force diagram for the beam loaded with 2-point loading. And this is a symmetrical loading. This loading is 20 kilonewton, which is at 1 meter from the right support, and this is 20 kilonewton 1 meter from the left support. And let us see what is going to happen. Support reactions are equal as the loading is symmetrical. Therefore RA equal to RB equal to 40 divided by 2, 20 kilonewton. Shear force values. Shear force just to the left of B, that is over here, is 20 kilonewton. It's going up, positive. And SF just to the right of D, same thing will continue just to the right of D, the value being 20 kilonewton, and we will cross the D for a bit. Then 20 kilonewton will be included, and here till here it is positive 20 kilonewton, and this is an addition of negative 20 kilonewton. Therefore it nullifies. The shear force to the left of D becomes 0. And same 0 value will continue just to the right of C, till just to the right of C, because there are no intervening forces. And when we cross C, and when we come just to the left of C, it is minus 20 kilonewton once again, and same minus 20 kilonewton will continue just to the right of A, just to the right of A, because there are no other intervening forces. And if we happen to plot this, interestingly, there is a portion of the shear force over here, positive shear force distribution amounting to 20 kilonewton, and here there is a negative shear force distribution. This is a atypical case of loading, and we have, by virtue of a selected kind of loading, we have made the portion of the beam, that is CD, spanning around 3 meters to enjoy zero shear force, because there is no shear force over here. Therefore, this problem is a pointer to indicate, by appropriately adjusting the loads, we can manipulate the value of the shear force. You can make it zero, or literally, in a literal sense, in a practical sense also. That means if you want to check the bending moment, the beam for bending moment, this is the way. So bending moment at B is 0. Bending moment at D is 20 into 1, 20 kilonewton meter, which is positive sagging. And same 20 kilonewton meter will continue till C, because there are no other loads. And it is a unit. See, bending moment at C is once again 20 into 1. We will come from this side. So 20 is the reaction, and it will lift the beam up. Therefore, it creates sagging. So 20 into 1, 20 kilonewton meter acts over here. So here also 20 kilonewton meter. Here also 20 kilonewton meter. Therefore, from here till here, there is a uniform value of the bending moment. So here exactly the beam behaves when we consider computing bending moment value at C coming from the left of the beam. That is, A reaction A is here 20 kilonewton. It will lift the beam up. And here it is 0. Here it is 20. Same 20 will continue till here, because we have computed bending moment to be 20 kilonewton meter from this direction. So this is a uniform distribution of 20 kilonewton throughout for the span of CD. Therefore, wherever shear force was 0 in the span length of CD, the bending moment tends to be uniform. Such a bending moment is called as pure bending moment. So bure bending moment sans shear force. And in the zone of the beam where pure bending moment exists, shear force is 0. So here is this kind of a loading will offer our laboratory studies to subject a beam to just bending moment alone, without the effect of shear force. Therefore, we will just characterize any material out of which beam is made as to how it behaves purely for bending moment. So this is traditionally called 2-point loading. So we define the pure bending moment. Pure bending moment is the uniform bending moment. We should add this uniformity, uniform bending moment, where shear force is absent or 0. So example 5, we will draw bending moment and shear force diagram for the beam loaded with UDL. Here is UDL, and we have already understood how UDLs will look like and how to treat them. Whenever UDLs are given, first of all, we need to convert it into equivalent load, and this equivalent concentrated load is the area of this special rectangle, where height of the rectangle is intensity of loading, and the linear dimension of the rectangle is 3 meters. That is the linear distance. Therefore, support reactions are equal because the loading is symmetrical, and the total load is 20 into 3, that is 60 kilonewton, and 60 kilonewton is being shared. 20 into 3 equivalent concentrated load divided by 2, and we will get the reaction to be 30 kilonewton. Now, shear force values. Shear force just to the left of B is plus 30 kilonewton. Just to the right of A is 30, the positive, minus 20 into 3, minus 60. Therefore, it becomes minus 30 kilonewton. And here there is a reaction of plus 30 kilonewton. Shear force of minus 30 kilonewton. Therefore, our computations are correct. And we will plot the shear force. Here it is positive 30 kilonewton. Here again it is positive 30 kilonewton. So this is a height, this is a straight line, and this has the height of 30 kilonewton, scaled height, and here also it is 30 kilonewton. So whenever a line is drawn with two perpendiculars at the extremities, and if we happen to connect them, that line will pass through the center. That means here at the center the shear force is 0. And we will just see how to connect these 2 points. So we will consider a fragment of a beam arbitrarily, which is subjected to W kilonewton per meter, and the section we have considered is at X meters from the right support, and here is the reaction R. And when we compute the shear force over here, it is R, which is going positive, minus W into X, WX, the equivalent concentrated load, which is going down. It is R minus WX. With a tweaking, with the adjustment of this particular equation, and if we assume SF equal to Y and WX equal to MX and R equal to C, this variation looks like a straight line with an intercept, of course. Therefore, the variation of shear force as far as bending moment is concerned over the beam, it is linear. Therefore, we will connect these 2 points linearly, and it will happen to pass through the center. Therefore, after drawing the shear force diagram, we have got yet another point apart from A and B. And this is a very important point because here the shear force is 0. And we will compute what is the bending moment value over here at a place where shear force is 0. We will find it interesting, and the bending moment happens to be maximum at C. Therefore, we will proceed for computing bending moment. So bending moment values: bending moment at B equal to 0 because it is a simple support. Bending moment at center, because this is recognized to be a very important point because shear force here is 0. It is 30 into 1.5. Okay, 30 into 1.5, we are considering the section over here, which is lifting the beam up, creating sagging, minus this portion of the UDL. It is 20 into 1.5, the equivalent concentrated load, which will be acting exactly at the center of the CB, center of CB. Therefore, the moment arm is 1.5 by 2. 1.5 by 2. Therefore, it gives us 22.5 kilonewton meter. So the reaction is lifting the beam up, positive, while UDL is making the beam to hog, to bend down. Therefore, it becomes negative. The bending moment caused due to UDL becomes negative. Right. We will plot this first. Okay. The bending moment here is 0. Bending moment here is maximum 22.5 kilonewton. And when we develop an equation for this, bending moment at C is reaction into X minus W into X is the equivalent concentrated load. X by 2 is the moment arm. Therefore, it becomes WX square by 2. Therefore, this looks like Y equal to AX plus BX square, which is typical of a parabola, which is typical of a second degree curve. Therefore, whenever UDL is acting, the variation of shear force is linear, while the variation of bending moment is parabolic. So whenever we draw the parabola, it looks like AX minus BX square. We should draw in such a way that it should always show convexity upwards. Whenever we draw bending moment variation for a beam subjected to UDL, and this variation happens to be parabolic, just now we have proved, and whenever we write the parabola, it is always convexity upwards. So now the sixth problem is bending moment and shear force for the beam loaded with concentrated moments. Here is a beam subjected to concentrated load, concentrated moment exactly at the center. We may wonder as to how we can generate concentrated moments at any point over the beam. It is very simple. We will just erect a brace, erect a frame, or we will weld a frame like this in a straight fashion, and we will apply the load like this. That will create a concentrated load at this particular point. Therefore, it is easy to create concentrated moments at any points over the beam, including supports also. Support reactions we will calculate. RA plus RB equal to 0 because there are no vertical forces acting down. And we will take moment with respect to A to be equal to 0. So it is minus RB into 3 because it generates anticlockwise moment plus 30, the applied moment, direct moment, because there is no moment arm to be again multiplied because it is the concentrated moment. So we will get, upon simplification, 30 by 3, 10 kilonewton. Therefore, 10 kilonewton is going up. And when we find RA, by substituting value of RB over here, we will find RA to be negative 10 kilonewton. Therefore, the force, the reaction is acting downwards, because we assume to be positive upwards. For the equilibrium, it has to safeguard the equilibrium, and there is an applied moment of 30 kilonewton in clockwise direction, and 10 kilonewton going up, 10 kilonewton coming down will create a couple once again, and it will create a kind of anti-clockwise moment worth 10 into 3. So 30 kilonewton meter anti-clockwise, while the applied moment is 30 kilonewton meter clockwise. They will nullify each other, and the beam AB will be still in equilibrium. So this is a mechanics concept, of course, and we worry the internal matter of a beam. Therefore, first of all, we have to ensure that the beam is in equilibrium, and we will ensure while we calculate the support reactions. So shear force at sections. Shear force just to the left of B equal to 10 kilonewton positive, and there are no other forces acting for the entire span. Therefore, we will just suddenly jump to just to the right of A. Just to the right of A is once again 10 kilonewton. It's the same positive effect. Therefore, the distribution of shear force is uniform over here, amounting to a magnitude of 10 kilonewton. Okay. Therefore, this is a positive shear force distribution diagram. And bending moment at sections. Bending moment at B equal to 0, we know this. And here, whenever concentrated moments are acting over a beam, we have to just stop for a while, and we need to treat this concentrated moment the way we treated concentrated loads while computing shear force. Therefore, concentrated loads is to shear force, and concentrated moments is to bending moment. And here we will just elude the effect of 30 kilonewton meter, and we will consider only the effect of 10 kilonewton, the reaction. It is 10 into 1.5 positive, which is lifting the beam up. So SF just to the right of C is 10 into 1.5, 15 kilonewton meter. If we just cross this, just to the left of C, we have a reaction into 1.5, 10 into 1.5 positive, so 15 kilonewton meter. We have to notice over here an anti-clockwise moment at this particular section created by 10 kilonewton. It will create sagging, and the given moment is clockwise over here, which will bend the beam downwards, creating hogging. Therefore, as far as bending moment is concerned, the nature of bending moment is concerned, 30 kilonewton meter will create hogging bending moment. Therefore, it should be treated as negative. Therefore, 10 into 1.5 minus 30 will give us minus 15 kilonewton meter. So here till here, just to the right of C, it is plus 15, and here it is, so this is pushing down, so it is minus 30 minus 15, so minus 15 is over here, and there is a transition. So the depth, the height of this particular transition, so from positive to negative, is equal to 30 kilonewton meter. The way in which we found for concentrated loads, the shear force at the place where concentrated load is acting happens to be a stepped function, and the height of the step will be equal to the loading itself, and here the intensity of load itself, and here the height of this particular step will be equal to the intensity of the moment. It is 30 kilonewton meter, this is 15, and this is 15. Therefore, the bending moment diagram will be just like this. And if you happen to compute the relationship, we will have at any typical section X, somewhere over here, we will have over here, it is 10 into X positive minus 30 equal to bending moment. Again, it's a linear relationship, Y equal to mx plus C. Yeah, this is bending moment diagram. So like shear force with concentrated loads, bending moment with concentrated moment is a stepped variation. The rise or drop of the step is equal to the magnitude of the moment, as it is seen over here, 30 kilonewton meter. The last problem in this particular tutorial happens to be bending moment and shear force distribution for a beam loaded with the concentrated moment as well as a concentrated load at the centrally. So here is a concentrated load of 20 kilonewton, concentrated moment of 30 kilonewton. Let us see what happens. So support reaction here equal to RA plus RB equal to 20, RA plus RB equal to 20. 20 is coming down, therefore, and we will take moment with respect to A. So we will have RB into 3 anti-clockwise moment plus 30, that the direct moment acting in a clockwise direction, plus the effect of 20 into 1.5, that is also clockwise with respect to A. Therefore we will get RB equal to 60 by 3, 20 kilonewton. And if we substitute RB over here, we will find interestingly RA equal to 0. So 20 kilonewton, 0 kilonewton. Anyway, we will just plot, we will just find the shear force values the way we have found in the previous problems. There is nothing special about this. So its shear force just to the left of B is 20 kilonewton positive. Just to the right of C, it is same. It will continue. Just to the left of C, it is 20 positive minus 20 negative. The shear force will become 0, and there is no shear force value beyond C till A is reached. So shear force here is 20 kilonewton positive. Same 20 kilonewton will continue uniformly up to just to the right of C. Just to the left of C, it is 20 minus 20 will become 0. Therefore, this is the only shear force value, shear force distribution. For the rest of the beam, shear force is 0. Yeah, we will try drawing bending moment values. Sketch the bending moment distribution diagram. Bending moment at B equal to 0. And here, as we did in the previous problem, we need to consider bending moment just to the right of C. Just to the right of C is 20 into 1.5, which is positive because it will lift the beam up, creating sagging. And it's 0 over here. Okay, bending moment just to the left of C. When we cross over here, it is 20 into 1.5 plus 30 minus 30. It becomes 0. So this is the just bending moment diagram. Okay, triangular distribution, which is positive. 30 kilonewton meter, and that is the height of the step. So this step height will be equal to the intensity of the moment. So bending moment at A equal to 0. So dear my respected viewers, with this we will make a summary of learnings. If the loading is sketched or written over here, and we are just we will just rehearse, or we will just let us say recall our memory as to the kind of variation for different types of loadings. If the loading were to be concentrated load, the variation of shear force is stepped, and variation of bending moment is linear. This is a very important thing to be remembered, okay, and recalled. And loading is UDL. If the loading is UDL, variation of shear force is linear, and variation of bending moment is parabolic. And as for if the loading is concentrated moment, variation of shear force is not applicable, because in no way concentrated moment to be considered for shear force computations. Okay, and variation of bending moment is stepped. So the way in which we treat a concentrated moment in bending moment diagram is same the way in which we treat concentrated load. Right. Another important point to be remembered is, in case of inclined loads, only vertical component is to be considered for computing shear force and bending moment. The horizontal component will be taken up by one of the supports, that is namely hinged support, and hinged support will have an opposite signed reaction. And if the applied horizontal force is positive going towards right, the reaction developed at the hinge will be negative coming towards left. Therefore, rightward force and leftward force of equal intensity will be effective in creating compression in the beam. And of course, compression, studying about the compression is not the cup of tea as far as bending moment and shear force is concerned. Therefore, we are unmindful of the dealing with horizontal components of inclined loads. So with this, we have completed simple problems specifically addressing simply supported beams with various kinds of the loads. And in the next tutorial, we will come up with a bit complicated problems considering all kinds of beams and all kinds of loadings. And until then, bye. And if you have liked this video, kindly subscribe to my channel.